Hey guys, this is Professor Janacek. I want to talk about vectors. A vector is a quantity with magnitude, which we also can think of as length, and direction. Now, in the world of vectors, if we're talking about just a number, we call that a scalar. A scalar is a quantity with magnitude, but it doesn't have a direction, so it's just a value. Let's talk a little bit about notation for vectors. Suppose we have the vector PQ. Now you'll notice I have this little notation above there. It looks almost like just the top half of an arrow to the right. Now this means that I have the vector that starts at point P, which we call the tail, and goes to a point Q, which we call the head. You could also simply call it by a single term, a single variable, which we'll often do. So vector W would simply be some vector out here, W, and I don't know the points necessarily where its tail and head are. We'll talk more about how to work with those vectors here in a sec. I want to look at some specific vectors. The zero vector we denote as a 0 with the little vector symbol above it. Sometimes in typesetting in your textbook, you might see it just as a bold-faced 0. So a bold-faced number or a bold-faced letter would be the notation for a vector. The 0 vector has a magnitude of 0, and its direction is also 0. The position vector, which we could also call the vector in standard position, could be any vector name. I'll call it V, but it has some special attributes. One, it could be written as V, or I could also write it as V1, V2 in these things that kind of act like parentheses, but the left one is more like a less than sign, the right one is like a greater than sign. That is vector notation. This tells me that I have a vector whose tail is at the origin, the point 0, 0, and its head is at the point V1, V2. Notice V1 and V2 are scalar values. I don't have the vector notation above them. And so basically this is a vector that starts at the origin and goes out to some point V1, V2. V1 and V2, those values, you'll notice are like the x and y values. So we say that they are the x and y components, respectively, of course. V1 is the x component and V2 is the y component. The unit vector has a special notation, so if we take a vector V and it's a unit vector, then we actually have the notation that we refer to as the hat over it. And a unit vector has a magnitude of 1. We also have coordinate unit vectors, and we'll use those quite a lot. Coordinate vector I, notice it has that hat over it, is the vector 1, 0. So its components are 1, 0. So its tail is at the origin, its head is at the point 1, 0. The J coordinate unit vector, notice it's the J with the unit vector notation over it, is the unit vector 0, 1. So its tail is at the origin and its head is at the point 0, 1. So you could actually draw these. The point 1, 0 is out here, so that would be my I vector. The point 0, 1 is up here, so this would be the J vector. Now if I have a vector, let's call it V1, I'm sorry, let's just call it V, but it's a vector made up of the components v1 and v2. Remember, v1 and v2 are scalars. They're not vectors. They're just numbers. I could write this as v1 times the I component, or I vector, plus v2 times the j vector, which could also be written as v1i plus v2j. Again, notice I'm using the unit vector, the coordinate unit vector notation. All right, what about equal vectors? Equal vectors have the same magnitude and the same direction, but they're not necessarily in the same location. So if I have a vector, say it's in standard position, so it's a position vector. Oops, things are getting moved around here. All right, let's try that. All right, suppose I have a vector here, again, in standard position. I could actually move that vector, say move it over here. As long as it's the same length and in the same direction, we call them equal vectors. Okay, magnitude. If we're looking in R2 space, let's take a vector. We'll call it V with components v1 and v2. The magnitude of this vector, notice the magnitude, I'm using the absolute value symbols. That is defined to be the square root of the square of its components. So it's the square root of v1 squared plus v2 squared. That might look kind of familiar. It is closely related to the Pythagorean theorem. So if we have a point in R2 space, let's call this x1, y1, and let's take another point, we'll call it Q, x2, y2. So point P has coordinates x1, y1, point Q has coordinates x2, y2. Then the vector PQ is, notice this is vector notation, it's x2 minus x1, comma, y2 minus y1. And if I wanted the magnitude of that vector, then it's the square root of x2 minus x1, parentheses squared, plus y2 minus y1, parentheses squared. That's in R2 space. What if we are in R3 space? Let's take a point. In R3 space, point P would have 3 coordinates because it's 3 space, so we'll call it x1, y1, z1. And let's take the point Q with coordinates x2, y2, z2. Then the vector PQ has the components x2 minus x1, y2 minus y1, and z2 minus z1. Yes, it has 3 components because it's in 3 space. The magnitude of this vector, again, notice I've got the vector notation. Every time I write a vector, I must write that vector notation above it. The magnitude of that is the square root of x2 minus x1, quantity squared, plus y2 minus y1, quantity squared, plus z2 minus z1, quantity squared. Notice that, oops, these two magnitudes, this is a scalar value. Magnitude is a scalar, not a vector. All right, a vector in the same direction as vector v with magnitude c can be found by taking c, divide it by the magnitude of v, because that's a scalar value, and then multiplying it by vector v. So if I want a vector in the direction of v but with a different magnitude, so same direction but different magnitude, different length, this is how we find it. We use this little formula here. All right, now what about direction? That's one of the other qualities of a vector. The direction is an angle, which we can call theta. It's the angle between the positive x-axis and the vector in standard position. So if I have a vector, put it in standard position, then this angle here is what we call the direction. Right? Hope that makes sense. Enjoy!